Hello everyone, my name is Francisco. I am one of the developers of AiiDA core here at EPFL. And in this video, I will show you a general introduction and overview to the code. So first, I'm going to give you a bit of context and talk about the motivation behind the development of AiiDA. And afterwards, we're going to go a bit into the code itself and how to use it. So most of you are already familiar with the exponential rate at which computational power has increased over the last years. Nowadays, we are actually at the verge of achieving speeds that are in the order of the exaflops. This, in turn, has allowed computational scientists to continually expand the horizons of their research, both in the precision of their results and in their sampling capabilities. And the material science community, from where we come from, has been particularly interested in these advances and in tackling the obstacles that come with them. So, one of these problems that is actually more widespread throughout the whole range of scientific disciplines, and which is particularly important to understand AiiDA, is the notorious reproducibility crisis. And reproducibility is one of the cornerstones of the scientific method, so this is not something to take lightly. It is easy to understand how this could be a problem in real-life experiments. This is because it is extremely difficult to have control over all possible variables that might be relevant. But computational scientists, however, have much more control over the environment of their simulations. So why is this a problem for us too? And to understand this, we first need to analyze and model how is the process of doing computational research. And for this, we will use what we call a provenance model, which in this case will represent the whole process as a graph of nodes. And we will see that this representation will not only help us to understand the problem, but will also help us when we're trying to solve it. And we will start, since part of our job is dealing with different pieces of information, we will represent this as contained inside of nodes that we will call data nodes. And as you can see, these nodes may contain, for example, a list of atomic positions that are the input for a molecular dynamic of the set of parameters for the code that we will use to do this dynamic. And and then the way we use this information is we transform it. We take an initial geometry and the list of inputs, we run the code and we obtain the relaxed geometry or a trajectory, so another piece of information. And the transformations themselves will be represented by these calculation nodes, whereas the whole process of transforming one data into another will be displayed by connecting the data nodes of the calculation nodes and the data nodes with directed lines. The direction of these links will depend on whether the data was used or produced during the calculation. So this would be a single step of computational research, and what it would look like represented this way. We see that the transformation of some initial data D1 into an output data D2 through the process calculation of C1. And it is important to note that there is information not only inside of the data nodes, but also on the links. And this information is about the relationship between the different pieces of data. Now, this is only a single step, but a scientific process or a scientific workflow will involve several of these steps, and many of them will be operating over data created by its predecessors, as here is doing C2 over D2. Then it becomes more evident how there is information on the links, as the same node, in this case D2, can act both as an output to the calculation C1 and also as an input to calculation C2. This then has to be considered when we are organizing our information. So, because when we do so, we normally use the architecture available to us in our computers. That is, in this case, the folder system. However, this system is not particularly well suited to store the information of the connectivity. And typically, we will have information of the data nodes inside files, but there are no calculation files. The calculations are just codes we execute or commands we run. So for example, one way in which many of us try to keep the information that two data nodes are connected through a calculation node is by making one folder per calculation and keeping there all the inputs and the outputs. So we can imagine that for a typical two-step workflow that consists on first generating some data and then analyzing it, one would end up with these two folders. The problem here is that while they do keep the link given by the calculation, they each need to have a copy of the file that contains the data D2. Hence, what we lose here is the connection between these two steps given by the output of them being used as an input by the other. In this minimal case, it might seem trivial to remember that these two folders correspond to consecutive steps, or even we can use symlinks instead of copying the files. But as workflows become more elaborate, then the workload on our memory and on the extra upkeep necessary to keep this information manually becomes just too much. And real-life scientific workflows look like this. So as you can see here, these are the steps, all the steps involved in calculating a single property for a single material. Here is a zoom window so you can get a better idea of the scale of this graph. And now it is easy to understand how high throughput projects require multiple properties calculated for thousands of materials would compound on this issue. So it is incredibly difficult to keep track of all of these connections manually. We need a tool that will help us keep track of the full provenance graph. So this is what has become one of our main focuses in developing AiiDA as a software to support high throughput projects. And with that in mind, let's take a look now at the system itself and how it works. So the first question is, what exactly is AiiDA? And AiiDA is a Python library that you can pip install in your working machine and will provide you with a set of tools to use for doing your research work. As users, you typically handle these tools either to a command line interface called Verdi or a Python ORM to be used either while writing script files or to a Python shell. We will now see how to handle this. And when you use these tools, you will be able to easily manage your calculations irrespective of where they are running, either locally or in a remote machine. And AiiDA will also keep track of the provenance for your work automatically. Here we can see how the different functions of AiiDA are organized internally. On the right, you have the different interfaces you can use to interact with the AiiDA installation. And you can see both the ORM and the command line, but there are some other options as well. On the left, you can see the engine that is in charge of managing the daemons that run in the background and keep track of your active calculations. And finally, it is also relevant to mention here below the internal storage consisting of a file repository and an internal database where all the information of the provenance is stored. So these are the pieces of the puzzle, but then how does it work? Or more specifically, how does one work with this? So, okay, let's take a look at this very simple procedure. We start with this initial piece of information, this initial data, the number 10 stored in our variable data 0. And we run two calculations or transformations on it. The first one is to multiply it times 2, and the second one to add 1. Very simple procedure. And you can run the script like this and maybe print the result to a file to be used later for other processes or keep it in a different fashion. But we have seen before, it is very easy to lose track of where this value of 21 came from. So the solution with AiiDA is that by introducing some simple adaptations that I will now explain into the script, we can now run with AiiDA in a way that will keep the provenance of this two-step procedure. And so if we run this with AiiDA using the command line tool, we call Verdi run with the name of the script, and AiiDA will start processing it. So the first thing that it does after reading the definitions is to create an initial data node, as indicated here to Python by using the AiiDA ORM type to store integers. And you can see that when it creates the node in the database, it assigns it an ID number to it, and we will see later why this matters. But then the next step is to use this initial data node as an input to our first calculation times 2. And you can see that the calc function decorator in the definition is indicating to AiiDA that it needs to keep track of the provenance by connecting the inputs and outputs of this function to a calculation node. Again, note that it assigns a different ID number to every node it creates. And finally, it calls the last function and generates the last calculation and final output. This works exactly as with the previous calculation. So finally, the script finishes, and our database will have kept the record of all the transformations that turned our initial value inside of node data 0 into our final value stored in node data 2. Now, the thing is that all of these nodes are kept inside AiiDA's internal database. So the user does not directly see any of this content. So the program also provides a series of tools to explore the content of your database. So for example, you can ask AiiDA to list all the calculations that it has recorded by running this command, Verdi process list, and expose the information about the two calculation nodes we just ran. So we had their ID numbers, their label, which here will allow us to identify each of them, and their state, which in this case is finished successfully for both of them. During this tutorial, you will learn how to run different calculations, how to read this status, but we just now focus on this. And if we wanted more details for one of them, we could take, say, node 2, for example, and we could run Verdi process show with that ID. And now we get even more information, including which are the inputs and the outputs and what are their IDs. So again, we also have a command that allows us to check the values stored inside of these data nodes, referenced by their ID numbers. And also, finally, in this case, we can obtain information about the process that these nodes underwent, because even if you lose the script file or you don't remember what the definition associated with this calculation node is, you can see that the information is stored inside of the calculation node itself. So you can always know that it's what this process involved. Now, hopefully this gives you a bit of an overview of how it is like to work with AiiDA, and how to use the ORM scripts and how to use the command line interface to run the scripts and to query the database. And note that what we just did here with Python functions can also be adapted to use almost any kind of external code, external program, only that instead of using a decorator, you will need to set up the information of how the code works in a way that AiiDA can understand it. In other words, you will have to implement what is called a calculation plugin. So AiiDA's core distribution is built as an easy-to-expand base that you can use to create wrappers around almost any external code. So you can use almost any external code this way by doing a calculation plugin. But calculations are not the only aspect of AiiDA that you can expand and customize. You can see that there are many other types of plugin, and the best part about this is that you might actually don't need to create yourself your own plugins, because AiiDA also fosters a community of plugin developers. So these are people who design plugins to deal with very well-known codes or very common data structures, which are then gathered into pip installable packages and published in the AiiDA plugin registry. In this tutorial, you will be running quantum space simulation, and you will actually do so through one of the plugins specifically designed to interact with that code. We are not going to go through all of the plugins now, but I do want to introduce you to one last important concept, and that is the one of workflows. Because we already mentioned workflows more colloquially in the intro when we talked about the scientific workflows and analyzed what they look like. So you already know that if you want to take a material and compute the band structure for it, there are a lot of steps involved. And I already showed you how AiiDA can automatically keep track this linked information for you. But it can actually do a bit more than that. So there is no need for you to manually do each of these steps that are pictured here. And this, of course, might already be apparent to you because when we saw how to work with AiiDA, we wrote our two-step mini workflow in a script. So it is natural to think, okay, why can't we do a script that does this whole workflow now? And indeed, this is possible with the tools that we have already saw. And it, not only possible, but also extremely valuable. Because not only does this make it easier to apply the workflow, both for reproducibility purposes, but also to repeat it and apply it to different inputs, but it also allows to hide both the computational and the scientific expertise or know-how from the end user, making this into a tool that you can now offer to a wider audience. We call these tools turnkey solutions, as you can just plug them in and turn them on, and they just work. Moreover, in AiiDA, we support the design of workflows through the implementation of a specialized type of node. So how does that work? Let's first analyze how one would go about doing this normally. You can imagine taking the procedure that we used before here. Here in the right is what we used before, and then wrap it around the function here on the left that can more easily be reused. So if we were to run this new script with AiiDA, then we would obtain the exact same provenance as before, as is expected. But again, with some simple modifications in the way that the script works, in this case, just a single decorator. And we can indicate to AiiDA that this function is defining a cohesive procedure. And so when we run this one, it will reflect this cohesiveness by connecting the initial and final nodes, as well as both calculations used, to a controlling workflow node. This way, not only does the origin of each of your results can be traced back to the data provenance, but also there is a logical provenance, in this case represented by the workflow node, that helps you to understand the bigger picture of your procedures. And so with this, we have now seen all the features that I wanted to show you. So to summarize, with AiiDA here, you will learn how to use it to locally control your remote resources and keep track of all your calculations directly from your computer, so without having to log in different clusters or copy files around. We will see, or we have seen how you can work in a way that the data provenance of your results is recorded and you have full traceability for your work. We will expand on this later. And finally, we have just saw how AiiDA also supports the implementation of high-level workflows and the design of turnkey solutions. So I hope now you have more concrete idea of what AiiDA is and how it works in general. So let me just wrap up by briefly showing you the funding agencies that support this project. You can also find here at the right some online resources available for you. And finally, this is the people who are currently involved in the development of the code, and also former members and active plugin developers. You will get to know some of these people in the next couple of days. So for now, I thank you for your attention, and I will see you later in our Q&As and hands-on sessions. Goodbye.